Hello
everyone,
everyone,
and
and
today
today
we'll be
we'll
seeing
be
one
seeing
of the
one of the
problem
problem
from
from
Geeks for
Geeks for
Geeks.
Geeks.
It
It
says
says
kth
kth
missing
missing
positive number
positive number
in
in
sorted array.
sorted array.
So,
So
given an
given an
sorted
sorted
array of
array of
distinct
distinct
positive
positive
numbers,
numbers,
integer
A
a r r, you need to find kth positive number that's missing from the array. Now, if case 5 and we are given array such like this, we have these many missing
these many
numbers:
missing numbers.
1, 5, 6, 8, 9, 10, and the fifth element from this is 9, and hence the result answer is 9. Similarly goes with second example where array elements are 1, 2, and 3. No array element is missing, and hence the next subsequent elements, which are 4, 5, 6, are the missing ones. And here, if case 2,
Case 2,
then the missing
then the
element
missing
is
element
5.
is 5.
So on and so
So on
forth.
and so forth.
Next, if we
Next,
go ahead, 1, 2, 4, 6 are missing elements, and second element is 2. That is the question. And we have to solve this with an expected time complexity of log n. How can we do this?
do this.
So, well, first of all, one thing which directly comes into our mind is the brute force approach, which one can go ahead and say that, hey, I'll have two iterators and one for array, or one for array and one for range. So as the range progresses and as the array elements meet, we would advance the pointers accordingly, or iterators accordingly. And the moment, and at those moments,
Those
we'll
moments
keep
we'll
track
keep track
of missing elements. And if missing elements is equal to k, then at that moment, whatever element from the range we get, we will return that. So that is a brute force approach, but it will go ahead and it will use the length of an array. Not to mention if the limit is too far, so it will go ahead and check the limit. So it will be O of max of k comma n in such a way. Can we optimize this? Yes, we can optimize this by using binary search. So how can we do a binary
do a
search over
binary
here?
search over here.
First thing first,
First thing
we need
first,
to
we need to
understand how
understand
this
how this
array is being stored. So let's take
So
an
let's take
example
an
2, 3,
example
4,
2,
7,
3, 4,
11.
7.
I'll take an example 2, 3, 4, 7, and 11 with an indexes as 0, or I'll start with 1, 2, 3, 4, or 5. That would make our things simple. So these are indexes, but I have added plus 1 for simplicity. Now coming upon misses, how can we get this?
Get this.
So
So
from till this point, how many elements
many elements.
are we missing? We are missing one element because till this point there can be
It
one,
can be
but
one,
there
but
isn't
there
anyone.
isn't anyone.
And at 3 there's still one missing, so I'm taking 1. 4, 1 missing. At 7 there are 2
There are
elements
two
missing.
elements missing.
Sorry, 3
Sorry,
elements
three
missing.
elements missing.
That is 1, 2, and 3, which means, sorry, 1,
One,
5,
five,
and 6, because 2, 3, 4 are present, 5, 6 are missing, and hence we have the 7th element. That means 3 numbers are missing. So I'll write here 3 numbers are missing. And for 5, that means 11, we have nothing but 6 elements missing. How did I calculate this? A simple way to understand this is we have 11 minus 5. So if everything was within a picture, we can get the range something like 1, 2, 3, 4, and 1, 2, 3, 4 as arrays. So this being array, this being range. So I'll call this as range, which is from the index itself. So, or I'll just say instead of range I plus 1, and I'll just call it as array, range or I plus 1. So yeah, we have got the
We have got the
understanding
understanding.
based on this. Mrs. How many numbers are missing till that point?
Till that point.
And we also have
We
k.
also have k.
Remember, this
Remember,
misses
this
would
misses
just keep on increasing. So these are in the monotonous increasing fashion. Now within a
Now
k,
within the
when
k,
we have a sorted list, you know better what can be the best solution. If case 5, we can just go ahead and take this 5 to this position, right? So we have k, which is equal to 3. Now, tell me at this point, you have 3.
3.
You have to go to 5 because we need to have k as 5. How many steps you need to take forward? So there are plus 2 numbers I have to do. I have to make so that I can get the appropriate number. So I am having a number as 7. 7 plus 2 gave me 9. So that was the case over here, and 9 was a missing number. So is
So
it
is it?
9 a missing number? That means our algorithm should tell us the apt position, and once we get the apt position, we should add key to it. So don't worry if things are not yet very clear to you. Things would be much more clearer when we get into our code. So right now we have a left L is equal to 0, R is equal to either length minus 1, and I'll use it A for simplicity, and while L is less than or equal to R. I'm having a binary search over here, so let's consider one element which I'll take as mid. L plus R minus L divided by 2. So we have a mid right now, and with this mid I'll count as miss count. missing count, or okay, I'll try to pull my missing count is equal to a of mid minus mid plus 1. Why mid plus 1? Because you know it very well. Mid is an index, and index starts from 0, whereas we want to start our counting from 1. So 0 plus 1 is nothing but I plus 1 what we are doing, where I is the mid. Cool. Now let's check that hey, if missing count is lesser than the provided k, and if it is lesser, we need to look further right. Look on right, because we wanted to get on the higher number. So left is equal to mid plus 1, else right is equal to mid minus 1. Similarly, but in the reverse fashion. Ultimately, the moment comes that this while loop would break, and once it breaks, we would have an appropriate position. Where would that appropriate position be? It would be on the right. So right plus k plus 1. Why right plus? Or I would say right plus 1 plus k. So right, since being an index, we have to do a plus 1 here and plus k. So it's very similar to, let's take another example over here, 1, 2, 3. And we'll get to know this in a way that we have 1, 2, 3 with index is 0, 1 and 2. Whereas our right and k is equal to 2. So missing numbers are 0, 0 and 0. And since these are zeros, our target or our end right would be 2. And once we have right is 2, k is 2, we just wanted to sanitize this right as r plus 1, which is equal to 3, and 3 plus 2 is 5. In this fashion, we would get with our missing number, kth missing number. So r is chosen because r was the appropriate position at that point where we can fit the k. So in this case, it would have been this point. So far so good. Let's compile this code. For any compiler errors, there seems none. Let's try to submit this. Cool. It seems that it has passed the rest all the test cases, and this was a very classic program, or it was a very new kind of program with binary search. So if you wanted to know more about binary search or